For this video, I think I'm just going to grab screenshots from my calculator to help me fill in this table. So the first equation we're supposed to graph is r equals 5 cosine of theta. So you can just type into your calculator 5 cosine of 0, 5 cosine of 60, 5 cosine of 90, 5 cosine 30. But we want decimals because we're going to be plotting these things here. So using the unit circle numbers isn't necessarily the most appropriate thing. But given that I'm going to go ahead and use my calculator anyway, I'm going to go into y equals and type in 5 cosine of x. But actually, since we're going to check the answer on our calculator at the end anyway, let's go ahead and just change the mode right now into polar. And then go into y equals, and I'm just going to type this thing in, 5 cosine of, hit the x button, it now says theta. So you could just graph it, but that'll give away the ball game too soon, so let's not do that. But let's go into table set, which is second window. Let's start the table at 0 degrees, that's what we want here. And let's set this delta table, the change in the table, to be 30 degrees, because that's how much consecutive terms differ by. And then you want to make sure this one says auto, so it automatically generates the table. So if we do second table, which is right up here, then we should have the numbers that we want. So I'm going to pause the video, grab some screenshots, but this is a real quick way to use your calculator to fill in tables like this. Okay, so I've got my table here. One thing I neglected to do before was change the mode into degree mode on my calculator. So the initial numbers I had were all wrong. So hopefully you caught that and changed your calculator to degree mode and got these numbers. So go ahead and fill in the table if you haven't done so, and then you can watch me plot points if you want. So the first point is at a radius of a theta value of 0 degrees and a radius of 5. So you go 0 degrees and out 5, and we land right over here. And the next point is at the 30 degree mark, and it's at about 4.3. So we go to 30 degrees and then somewhere between the 4 and the 4.5 line. 60 degrees, 2.5. That's here. What's next? 90 degrees and 0. So what does that mean? Well, if you're going 0 away from the origin, you're going to land there at 0. But the 90 degree business really means that actually as you connect the dots here, you're actually coming in perpendicular to the x-axis. You're coming in along this y-axis, as opposed to, say, curving in this way, where this is the angle you come in on. Here's the angle you come in on. So that line should actually be tangent to the circle at that spot. Okay, moving on to the next point. What do we have next? 120 and negative 2.5. So I'll go to 120. 120 is here. But instead of going to 2.5, which I guess would put me around here, I actually need to go the opposite direction on that same line. So on the 120 line, which is really the same as this line down here. So we're going 2.5 there. So right in here is 120 and then negative 2.5. Okay, the next one is 150 and negative 4.3. So let's see, 150 and positive 4.3 would be somewhere around here, but we need to go diametrically opposite. We need to go backwards from that point. So then somewhere around here. And we'll erase that. And then the next one is, 180, negative 5. Okay, so if it were 180 and positive 5, it would be here. But instead of going in that direction, we go opposite, and we land right back at the starting point. And then we'll connect the dots and get some curvy looking thing that comes in this way. And goodness, it looks quite a bit like a circle. And then if you continue, I think we're going to see something funny happen here. So I'll draw one more dot. But if I wanted to go to, for example, 210 and negative 4.3. So let's pretend it's positive 4.3. So we go to 210 and then positive 4.3 is somewhere around here. But instead we go to the opposite point, and that lands us right over here. And so in fact, I think we'll end up just tracing this circle twice if you go from 0 degrees to 360 degrees. So that's what it looks like by hand. And I guess we can use the calculator to confirm. So if we come over here and we go to graph, but before we go to graph, let's think about the window. So first we want 0 to 360, and let's go up by, say, every 5 degrees. And then if we want it to look like the graph that we're looking at here, then negative 5 to 5 is what we should be doing there. And so we'll just hit graph, and we'll see our circle And then it's hard to see it getting traced again because it just lands on itself. So if you really want to see it get traced twice, then come over here and hit the enter key a few times. So that'll make it thicker. And enter again gives us this thing that looks like a key. That's the one that I want. Hit graph now, and we'll see the little circle attached to the key, and it traces out the graph, which is a circle, but then you can see it tracing out again. And so this is a nice way to see if something really is landing on top of itself. Okay, moving on to number 2. So I guess that means that in polar land, equations of circles look like r equals 5 cosine of theta. You might refresh your memory about the equation of a circle in xy land, and I contend that the equation of a circle in polar land is a whole lot simpler than the xy equation of a circle. Okay, the next one, r equals 2 minus 2 sine of theta. Apparently it's called the cardioid. So same thing as before, I'm going to go ahead and grab some screenshots. So first I'll just plug into this y equals thing. I think all of my modes are good now. If I go into table set, okay, that still looks good. So second table, don't graph it yet. So I'm going to grab some screenshots of these numbers and then come back. So go ahead and fill in the table and then pause the video, fill in the table, and then come back. Okay, so I've got my points here, and then we'll go ahead and graph them. So the first one is 0 degrees and out on the 2 circle. So I think that means we start right out here, and then 30 degrees we're at 1. And I think that's good. And then at 60 degrees we're at 0.2, which isn't very big. So at 60 degrees is pretty darn close to the pole, otherwise known as the origin. So 0.2 is maybe in there. And then at 90 degrees actually is at the origin. So we get something kind of like what we had before, something kind of round and curvy. It doesn't quite look as circular as the other one did, but let's see what happens when we continue. So the next one is 120 and 0.2. 120 and 0.2. So 120 and then at 0.2. So that means we're out like here. And then the next one is 150 and 1, so there's some kind of symmetric thing happening. And then 180 and 2 is out here. So I'll go ahead and connect the dots. So we've got something like that. And then 210 gets all the way out to 3. Okay, that's a surprise. So 210 to 3. And then 240 is at 3.7. 270 is at 4, so that's way down here. And then what else? 300 is back at 3.7. 330 is at 3. And then 360 is back at 2, which is the starting point that we had before. So we'll connect the dots here. So it comes down this way and then goes back up this way. And you might have already been able to predict the kind of shape we were going to get, given that the name is a cardioid, but it is so named because it looks like the way we draw hearts. Okay, let's see what the calculator thinks about the graph of this guy. So it kind of really takes a long time to get out away from the pole, and then it starts to zip around. So it's really moving quite a bit faster here. But I think that that looks pretty good. Number 3, r equals theta, which is called an Archimedean spiral. On this graph, the r equals 1 circle stands for r equals 100, and the r equals 2 circle stands for r equals 200. So apparently the r values are going to get big pretty quick here. So 1 is now 100 and 2 is 200. So let's type it into the calculator, just r equals theta, and then we'll go into second table. And again, I'll go ahead and grab some screenshots from here, so pause the video. Although actually this is pretty easy, right? If r is equal to theta, then these numbers just get copied. Okay, forget the screenshots, we can just write these ones in. So I filled them all in. Now we're going to plot some points. So at 0 degrees, we're at the pole right there. At 30 degrees, we're out at 30. But remember now that this half line really means half of 100. So this is the 50 circle right here. So we're only going 30 away. So we're going to be inside of that innermost circle. So at 30 degrees, we're 30 away. So maybe something like there. And then at 60 degrees, we're 60 away. So that's just a little bit outside of that red circle I drew. Be there. At 90 degrees, we're at 90, which is just inside of the 100 circle there. 120 degrees, we're out at 120. So maybe there, roughly halfway between the 1 circle and the 1.5 circle. At 150, we're at 150, so that's perfectly on this, at that point right there. 180 is at 180, that's here. 210, 210, maybe there. 240, 240, that's just inside the 2.5 circle. 270, 270, so that's around here. 300, 300, so that one we can find, that's on the grid. 330, 330, so around there. And then finally 360, 360, so that's about here. And so we'll connect the dots, starts at the pole, and we get this very nice spiraling outward type thing. And it's called an Archimedean spiral. And let's see if the calculator agrees with what we got there. Now, if we just hit graph right now, it's not going to work for us because our xmin and xmax and ymin and ymax aren't set the way we mean. So we really mean for it to be negative 500 to 500 on both. Maybe we'll put little dots every 100. So let's hit graph and take a look. I'm actually going to change the, oh no, we're fine. So let's hit graph and we will see the Archimedean spiral drawn out. It's there. Why does it stop there? Well, it stopped there for us because we went up to 360, and it stopped there for the calculator because we told it to stop at 360. But if, for example, we change this to 720, then we should see this thing continuing around. So there's the first spiral at 360, and then it looks like it kind of goes off the screen, but you can play this game and just change your window and see as many loops of this spiral as you want. I'll leave it as an exercise if you're interested in changing the theta min from 0 to some negative number like negative 360. Question is, what happens to this spiral if you allow theta to go negative? So you might try plotting a few points and then checking your answer on the calculator. Okay, the last one, r squared equals 25 cosine of 2 theta, apparently is called a lemniscate, and it says depending on the value of theta, there may be 2, 1, or no choices for the value of r. All right, so this one seems trickier. So let's see if we can use the calculator to help us. There's an extra column here. First, we'll calculate r squared, and then we'll find r. Okay, so let's go into the r equals, and we'll type in what the r squared is, 25 cosine of 2 theta. And then I'm going to look at my table. Don't graph it, but just look at the table. So we're going to fill these guys in. So these are the r squared values. So I'm going to write them in by hand. So pause the video and fill in this first column, and then come back. Okay, so we've got our r squared column filled in. Now we need to find r, which is just the square root of each of these numbers. So the square root of 25, well, it could be 5, but it could also be negative 5. Square root of 12.5, I'll just type that in over here. So about 3.5, but it could also be negative 3.5. And then we get to the square root of negative 12.5. Well, this isn't real, so I'm just going to put like a dash here. And same thing with negative 25 and negative 12.5 down here, so we're just going to put dashes there. And then we get to 12.5, which we've done already. 25 is plus or minus 5. 12.5 again. Not real, not real, not real. And we get that. Okay, so let's see if we can very carefully plot these points. So the first one is that at 0 degrees, we're supposed to be at 5. So 0 degrees 5, I can handle that. That's over here. And we're also supposed to be at negative 5. That's kind of strange. But anyway, those are the 2 points. Then we move to 30 degrees, and we're at 3.5. So we'll go to 33.5, which is on the grid right there. And then 30, negative 3.5. So that means you go to the opposite point. So negative 3.5 would land us out here. Okay, then at 60 and 90 and 120, the thing doesn't exist at all. So somehow it blinks out of existence, only to come back at 150. Okay, so let's plot. At 150, we have 3.5. So 150, 3.5 is over here. over here. And then we also have 150 negative 3.5, which is the opposite point. So I think that's right there. And then what do we do? At 180, we're back at 5 and negative 5, which I think are just the two endpoints that we have. So 180 comma 5 is this one, and then 180 negative 5 is this one. Are we going to get any more points here? Let's see. What about at 210? At 210, we're supposed to be at 3.5 and minus 3.5. So at 210, 3.5, that's this guy. And then negative 3.5 is that one. So it seems like we're just back. Let's see, so that was that one. And then we're back around here. 330 is at 3.5. 330, 3.5, yeah, that's right there. And then the negative is right there. And then the last one is 360. We're supposed to be at 5 and also at negative 5. Goodness, so we don't get any more information here. It's hard for me to know exactly what this is going to look like. Is it just kind of like this big elliptical thing? There's kind of this big question as to like what happens in this empty space. Like I can buy that it's going to hit these points here. It's going to hit those points there, but I really don't know what's happening in the middle. So I kind of feel like we need some more data. So how about we grab some more data? It just feels like the table doesn't give us enough information. So how about we look at theta and r squared and r. But what if we look at 15 degrees? So if I want to type in 25 cosine of 2 times the 15 that I just made up, then we get about 21.65. And then r is going to be the square root of that number. So about 4.7. Okay, let's, and also the negative, right? Okay, so these are more points. Let's plot these points. So at 15 degrees, we're going out to 4.6. So I'm going to plot these in another color. 4.6 at 15 degrees. So we're there. And then at 15 degrees, we're also supposed to go negative 4.6, which I think lands us out here. Okay, so that seems reasonable. We're just kind of filling in and getting more detail on what's happening in here and out here. But I guess I really still want to know what's going on in that space there. So how about we focus on the part after 30 degrees, but before the thing ceases to exist at 60. So maybe we can try 45. Okay, so 45 degrees gives us 0. I feel like that's silly. I think I should have known that one. Let's see. So that's a 0, and then the square root of 0 is 0. Okay, fair enough. Let's plot that point. So at 45 degrees, we're at 0. 45 degrees is, okay. So then apparently this curve comes in and actually has to hit the pole, but it's got to do it at 45 degrees. So I'm going to draw in the 45-degree line, and I'm also going to draw in the negative 45-degree line. And now I start to feel like I kind of have enough info. If you want some more points, then maybe pause the video here and try typing in like 40 degrees. That might be good information, or 35 degrees. So pause the video, plug those things in, you'll get a few more points, and then come back when you're ready. Okay, so then I think what's happening here is if we connect all these dots, so I think we started out here and then we went up this way and then we come in at the pole, and I just want to be clear, I didn't come in at 90 degrees. I'm actually tangent to the 45-degree line there. It's a small detail. And then it's got to go someplace. Now, I didn't do such a good job of labeling which points came in what order, but I think it's just going to shoot right on through the origin to this part next. And then it's going to loop back around here and then go back through the origin and then come back and finish that first petal. So I think we're going to get this kind of figure 8 infinity symbol, and I think it's going to be drawn in the order that I just drew. That is to say that the first part is this first quadrant part, and then the second part is down here, and then the third part is over there, and then the fourth part is there. Okay, let's cross our fingers and see what the calculator has to say. So we've got that thing typed in. What I really want to type in is the square root of that thing. And I also want to change my window. So 0 to 360 is fine. And negative 5 to 5, I think, is good for this. Okay, so let's hope that it looks something like this, and then we're looking again for not just the final product, the red curve, but also the order. I think it goes 1, 2, 3, and 4. There's 1, and I was wrong. And it's kind of interesting. So it went 1, 2, 3, 4, just in the order of the quadrants. Again, I didn't do a good job of labeling which points came when, but it was interesting. And we'll look at this thing again. I'm just going to put in a +0 here so the calculator has to redraw it. But I want to point out that there is a pause in the drawing of this thing where the calculator doesn't seem to be doing anything. So let's watch for that. So it draws and then it pauses, and then it draws and and then it pauses there, and then it draws again. And I think that that pause is when the calculator is handling the square root of negative numbers business. So there was a pause there, and then another pause way down here. Okay, so that curve right there looks very different from any curve we've drawn in XY land, but apparently that's the curve you get when you graph this thing right here. I'll also point out that on the next page, there's a little teaser here. If you change your equation to this complicated thing, very carefully type that in, change your window to these things, the 6.28 leads me to believe that we're looking at a 2 pi in there. So change your calculator mode back into radian mode if you're going to do this, but see what the graph looks like. Apparently it's a nice graph.